Hello everyone, today we'll start a new topic, asphalt technology. In this lecture, we'll focus on the introduction about the properties of the asphalt, which are related to the pavement design. Asphalt is also known as bitumen. It's one kind of materials which is majorly consists of hydrocarbons. It also contains a small amount of sulfur, nitrogen, and oxygen, and a trace amount of metals such as vanadium, nickel, iron, magnesium, and calcium. Typically, 82 to 88% of asphalt is carbon, 8 to 11% is hydrogen, 0 to 6% is sulfur, 0 to 1.5% is oxygen, and 0 to 1% is nitrogen. Usually, the characters of the asphalt can be measured with three tests: penetration test, viscosity test, and shear modulus test. These tests can measure the stiffness or the hardness of asphalt, and this character is very important for the pavement design. Asphalt actually refers to the black cementitious materials. It could be solid or semi-solid at normal temperatures. Usually, asphalt can be found as natural deposit or are produced from petroleum crude. There are three types of the asphalt. The first one is natural rock asphalt, which are rock deposits containing bituminous materials, and they are widely applied for road surface in locality where they are available. The second one is native asphalt, or we call the lake asphalt. They are obtained from asphalt lakes in Trinidad or some other Caribbean areas. These asphalt are used in some of the earliest pavements in North America. The last one, which is also the most common one, is the petroleum asphalt. They are the products of the distillation of crude oil. The petroleum asphalts are usually produced from the residual metals in the crude oil, which is extracted from the distillation process. In general, higher grade crude oil with less amount of residual metals will contain as little as 10% asphalt. For lower grade crude oil, is able to contain as much as 90% of asphalt. The figure on the right shows the distillation process, actually based on the residual metals obtained at the different steps in the distillation process and different materials added to the residual metals. We can get different types of the petroleum asphalts. In general, there are three types of petroleum asphalt applied for road pavement: asphalt cement, emulsified asphalt, and liquid or cutback asphalt. The first type, asphalt cement, is also called paving asphalt, which is one of the most popular materials applied for road pavement. The asphalt cement is the primary asphalt product from the distillation process of crude oil. At the ambient temperature, asphalt cement is a black, sticky, semi-solid, and highly viscous material. There are actually a lot of properties of asphalt which make it suitable for road pavement. It's strong and durable with excellent adhesive and waterproofing properties, and is also highly resistant to the actions of acids, alkalis, and salts. With that, it can support the pavement at different environmental and traffic conditions. Also, the asphalt cement can be easily heated and mixed with aggregates to produce the asphalt concrete, and asphalt concrete could be used for the construction of flexible pavements. Based on consistency in viscosity and penetration of the asphalt cement, we can classify the materials into several standard grades. There are actually two methods based on these two types of the consistency for the classification. If we use the viscosity grades, then we can classify the materials into 5 groups based on ASTM D3381 standard. We have AC 5, 10, 20, 30, and 40. If we apply the penetration grades, then we can use ASTM D946 to classify the asphalt cement. Depending on the penetration grade, we have the group as 200 to 300, 120 to 150, 85 to 100, 60 to 70, and 40 to 50. Generally, higher penetration indicates softer asphalt cements. So here, 40 to 50 is the hardest grade for the asphalt cement. The second type of petroleum asphalt is emulsified asphalt, which is also called emulsion. It's actually a mixture of asphalt cement, water, and emulsifying agent. We know that the asphalt cement cannot dissolve in water, so if we add the water to the asphalt cement, the asphalt and the water will exist in separate phases. In this figure, you can see that with the water, the asphalt cement will form perfect spheres. So in order to mix the asphalt cement with water, we need to add an emulsifying agent. Usually, it could be some types of the soaps. The figure here shows the process of producing the emulsified asphalt. Basically, we will let the hot asphalt cement and water containing the emulsifying agent passing through the colloid mill. And the colloid mill will break up the asphalt cement into very fine droplets in the water carrier. When the emulsified asphalt is used, the emulsion cells as the water evaporates. Also, the emulsion usually contains 55 to 75% of asphalt cement and up to 3% of emulsifying agent, and the rest is the water. ASTM defines two commonly applied emulsified asphalt. The first one is defined in D977, which is anionic emulsion. It has electronegatively charged asphalt droplets. The second one is defined in D2397, which is cationic emulsion. It has electropositively charged asphalt droplets. Usually, the anionic emulsion can adhere better to aggregate particles with positive surface charge, such as limestone, while the cationic emulsion can adhere better to aggregate particles with negative surface charge, such as sandstone, quartz, and siliceous gravel. The cationic emulsion can also work very well with wet aggregates and cold weather. Both emulsions can have the rapid, medium, and slow settings, which are specified in the ASTM D977 and 2397 standards. The table here summarizes the cases of using emulsion with different settings. Basically, for surface treatments and penetration mechanisms, we have to consider rapid setting of emulsion. For open-graded cold asphalt aggregate mixture, we need to consider medium setting. For track coat, fork seal, dense graded cold asphalt aggregate mixture, and slurry seals, we need to consider slow setting. The last type is liquid asphalt or cutback asphalt. They are usually made of asphalt cement mixed with the solvent to reduce their viscosity. In that sense, they can be easily applied at ordinary temperatures. In reality, the liquid asphalt can be heated and sprayed on aggregates directly. Also, once the solvent is evaporated, the asphalt can cool or harden and cement the aggregate particles together. In addition, based on the types of the solvent and the rates of evaporation and curing, the asphalt can be categorized into three types. If the gasoline is added to the asphalt cement, we will have the rapid curing asphalt. They can be used primarily for track coat and surface treatment. If we add the kerosene to asphalt cement, then we will get the medium curing asphalt. They are generally used for prime coat, stockpile patching mixture, and road mixing operation. Finally, if the diesel is added to the asphalt cement, then we will generate a slow curing asphalt. They are also called road oil. They are generally used for prime coat, stockpile patching mixture, and dust palliatives. The asphalt actually has a lot of properties which are very important for road pavement design. In this page, I list a set of properties we should put into the consideration, including consistency, specific gravity, ducticity, purity, flash point, rate of curing, aging or hardening, resistance to reaction with water, durability. In the rest of this lecture, we will make a brief introduction about each of the property. The first one, consistency, actually describes the degree of fluidity of asphalt cement at any particular temperatures. Usually, the consistency is measured with viscosity and the penetration rate of asphalt cement. The definitions of these two terms will be introduced in the rest of this lecture. In addition, we also need to think about the softening point, which is the temperature when the asphalt cement changes its phase from solid to liquid. The consistency in viscosity is applied to measure the resistance of the asphalt cement to flow, and is the fundamental consistency measurement in absolute units. In the field experiment, there are a lot of methods applied to measure the viscosity. Based on the ASTM standard D2171, we are able to measure the absolute viscosity at a temperature of 140 degrees Fahrenheit. Also, from the standard D2170, we can get the kinematic viscosity. Usually, the kinematic viscosity equals to the absolute viscosity over the density of the asphalt cement. In addition, for the viscosity, if the temperature increases, we can see that the asphalt cement will become more fluid and the viscosity will decrease. Also, a very viscosity fluid will usually be very thick. The figure here demonstrates the relationship between the kinematic viscosity with respect to the temperature for three different types of the asphalt cement. Clearly, we can see that with a higher temperature, the kinematic viscosity will be smaller, and you will observe the linear relationship between the viscosity and the temperature. The penetration test is an indirect method to measure the consistency of the asphalt cement empirically. The figure on the right shows the procedures to conduct the penetration test. Usually, the penetration is expressed as the distance in tenths of a millimeter that a standard needle penetrates the sample of the asphalt cement vertically under standard conditions of loading, which is set as 100 grams. A standard time, which is 5 seconds, and a standard temperature, 77 degrees Fahrenheit. The softening point of asphalt cement is usually measured by the ring and ball methods, which is defined in ASTM D36 standards. The figure below shows the setting of this method. In general, the softening point can be simply be identified as the temperature at which the asphalt cement cannot support the weight of the steel ball and starts flow. With that, we can identify the temperature when the asphalt cement changes phase from solid to liquid. The specific gravity is another important property of asphalt cement. We have already provided the equation for us to calculate the specific gravity in the tutorial 3. In general, the procedure of determining the specific gravity and density of asphalt cement is defined in ASTM D70. We know that the volume of the asphalt cement varies with the temperature, so in order to find out the specific gravity of the asphalt cement, we have to find out the value at a given temperature. Usually we set the temperature as 77 degrees or 60 degrees Fahrenheit. However, for petroleum asphalt, we usually have the constant specific gravity. The value is very close to 1. Usually the value varies from 0.95 to 1.05. In addition, the specific gravity of the asphalt also decreases with increasing temperatures. For example, for the asphalt cement, it has a specific gravity of 1.0176 at a temperature of 10 degrees, but it's 1 at 60 and 0.9187 at 300 degrees Fahrenheit. Another thing we should know is that the specific gravity is very important to determine the percentage of the voids in the compacted materials, which will be very important for us to learn the superpave. Also, we can use the specific gravity to convert the volume measurement of the asphalt to the unit of mass. The ducticity is another important property of the asphalt cement. The procedure of ducticity test is defined in ASTM D113. The test will measure the distance in centimeters that a standard brick of the asphalt cement will stretch, which is at a constant speed of 5 cm per minute at a standard temperature of 77 degrees Fahrenheit before breaking. And with the estimated ductility, we are able to identify the potential adhesion and cohesion of the asphalt. Here, the adhesion is the ability to stick to the aggregate particles in the asphalt concrete, while the cohesion is the ability to hold the aggregate particles firmly in place. The purability of asphalt cement is applied to measure the amount of the pure bitumen in the asphalt cement. Usually, we have to apply refinement about the asphalt cement to increase the percentage of pure bitumen. With this kind of refinement, the refined asphalt cement will consist of almost pure bitumen, which is by definition is entirely soluble in carbon disulfide, while we can only allow a very little amount of the impurity in the refined asphalt cement. Usually, the purity of the asphalt cement can be determined by a solubility test, and the procedure of this test is defined in ASTM D2042. In asphalt cement, if it's heated to a high enough temperature, it will give off enough vapor to flash in presence of spark and open flame. The flash point is then defined as the temperature below that of the fire point, which is also the temperature where the materials combusts. The ASTM D92 defines the procedure of the flash point test to identify the temperature when the asphalt cement may be safely heated without the danger of instantaneous flash in the presence of an open flame. In asphalt cement, the curing is the process of evaporation of solvent from cutback asphalt and the attendant thickening of the material. Usually, the curing can be described as the change in consistency of the asphalt cement due to the progressive loss of diluent by evaporation. The rate of the curing is usually measured as the time required for a cutback asphalt to harden from its original liquid consistency and develop a consistency that is satisfactory for the function as the binder in pavement. There will be a lot of factors affect the rate of the curing, and the page here shows a list of the important factors we need to consider, including volatility or evaporation rate of the solvent, the amount of solvent, penetration or viscosity of the asphalt base, temperature and humidity of the environment, wind velocity, surface areas of the pavement, and so on. Aging or hardening of asphalt cement is another important property we have to consider for the road pavement design. Basically, aging or hardening is the process under which the asphalt cement becomes harder and brittle due to the increase in the viscosity of asphalt cement. In general, there are two major causes about the increase in the viscosity. First, the short-term aging is usually caused by the evaporation and oxidation of the lighter oily constituents during mixing at high temperatures. Second, the long-term aging is caused by the oxidation of the oil to resin and resins to asphaltants when used over a period of years about the asphalt cement. The figure below shows the viscosity under different temperatures at 2 different years. We can clearly see that the viscosity of the asphalt cement increase dramatically from the time of the construction to several years after the construction. In addition, we can see that the aging can significantly reduce the durability of the road pavement. In that sense, we have to put the aging seriously in the consideration about the pavement design. We know that water content has a significant impact to the performance of the pavement. In that sense, the asphalt materials designed for the pavement should be able to withstand the effect of water. Usually, the durability of the pavement is greatly affected by the ability of the asphalt to adhere to the aggregate particles in the presence of the water. In that sense, the loss of the bond in the presence of the water may lead to the pavement deterioration, and this one will significantly reduce the performance of the pavement. The last property of asphalt cement we want to introduce is durability. Generally, durability is defined as the property that permits the pavement materials to withstand the detrimental effects of moisture, air, and temperature. Usually, the performance and durability of the asphalt pavement are affected by a number of factors such as mix design, property of aggregates, workmanship, and the property of the asphalt. In general, we can summarize three major causes about the failure of asphalt pavements. The first one is permanent deformation or rotting, which is caused by the high temperature, and at a high temperature the asphalt will become softer and the mix will lose elasticity. The second cause is the fatigue cracking due to the high volume of the loading applied on the road and the edging of the asphalt. And the last one is low temperature cracking. When the temperature is low, the asphalt becomes brittle and the pavement shrinkage in cold weather. The asphalt cement should be designed and it should be mixed with appropriate aggregates to overcome these three potential causes. So that's all about the lecture today. Thank you very much for your attention. In this lecture, we learned the properties of asphalt cement, which can contribute to the future lectures in superpave. So start from the next lecture, we will learn the topics in the design with superpave.